Clickable Calculus, Differential Equations. In this webinar, we'll look at items in a differential equations course through the lens of Maple, noting the extent to which Maple enhances the pedagogy. One of the first topics in the differential equations course would be the notion of a direction field. So let's get the direction field for this differential equation. I'm going to make use of a task template. I'll show you where they are. Tools, tasks, browse. Brings up the table of contents here. There's 347 such task templates. We're going to go here to differential equations, ODEs, direction field. So this is the task template you inserted by clicking one of these two buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make the thing work. I've got the task template already embedded. There's the path that we just followed to get to the task template. Okay, here's a differential equation. We would like to get this. Let's grab this. Do a Control C for a copy. Let's paste that in here and hit the Enter key. Let's keep the ranges 0, 1, 0, 1, and all I do is hit the Enter key. Now here you see a command, the plot. All you have to do is hit the Enter key. You don't have to know what the syntax is. You don't have to look it up. The data that we've entered here is being accessed through these equation labels. Hit the Enter key. So there's the direction field for that differential equation. Now you can add a list of initial points. So I have 4 initial points, which is in the form of a list of lists. These are points along the vertical axis here. If you re-execute the command, accessing that list, you have equation label 4, it's picking up that list from here. Then you will get solution curves emanating from those initial points following the arrows of the direction field. 2 other terms that come up early in the differential equations course are the terms Nullcline and Isocline. So let's take a look at what these words might mean. Nullcline is a curve along which the derivative is 0. So this expression tells you the derivative at each point. We want to know what is the curve along which that derivative is 0. So I've brought down the function. It's just a graphing problem. I'm going to go here to the context panel, pick plots, 2D implicit plot. Order of the variables is xy. So this is the curve along which the derivative is 0, called nullcline. Now the isocline is a line along which the derivative is constant. So these are the level curves, or level sets, I like to call them level curves, of this function f. And we can look at that graph in one of 2 ways. So here I've brought the expression down. If we go to plots, 3D plot. Okay, so here's the graph. I can modify that surface. Let's put level curves on it. Okay, so you can see how those level curves form a contour plot. And you can see the values of the function along those curves. And the other way that you can obtain that contour plot would be make use of this plot builder tool and ask for a contour plot, a 2D contour plot. And so now you get a contour plot, which is equivalent to that graph there. So isocline, nullcline. For those inclined to study Picard iteration, it's the basis for one of the elementary proofs of existence and uniqueness. Here's a task template for creating Picard iterates. Now I showed you where the task templates are. There's the path to it. We need to fill in the fields on this task template. So right here we want to get x squared plus y. I've already put it there to save some typing time. The point about which we are going to generate these solutions. A is 2, that's this 2 right here. Initial iterate I've taken to be 1, and I'm setting the number of iterates to 5. So I just need to hit the enter key here to execute these lines. And this loop will create some iterates. You can see here I'm integrating the previous one to get the next one. Some lines here to print this stuff out in a nicer form. And I have indicated that this is what you will get for the Picard iterates. It's interesting to compare these Picard iterates to the exact solution. So let's find the exact solution and make a comparison. So here's the differential equation, and here's the initial condition. If we make use of the context panel, you'll see a solve the dE for y of x. So now we have the solution. Now, we can graph the solution if we grab this right-hand side. So let's pick the right-hand side. And now we can go to the plot builder, either here or down in plots. Go to the plot builder. I'm going to get a graph. We might want to modify the domain. See, the default is minus 10 to 10. Let's look on 2 to 5. So here we make this a 2, and here we make this a 5. And we get that graph. What do the iterates look like? Well, let's just take one of them. I'm going to do a copy, and I'm going to do a paste. And you can see initially they're quite close, and then they tend to drift apart. So you can put as many of those onto the graph as you like, get some idea of how the convergence of the iterates to the exact solution takes place. As Maple goes about solving equations, it has to figure out what kind of equation. So that ability to classify the equation is available to the user. There's a task template. Now I showed you the path to the task templates. I've put in this differential equation here. This is the command, but all you got to do is hit the enter key. Maple analyzes this and discovers that it's a Bernoulli equation. If you set info level of desolve to a higher number, if there are breakpoints built into the code, then when you execute a given command, you'll get a printout of some of those results sitting at those breakpoints. And then I set it back down, set info level back down so it doesn't disturb the rest of our work. And you can see what Maple has done. It has tried a quadrature. Look, is it first order linear? Then it tried a Bernoulli. Bernoulli was successful, and it prints out the solution. This classification functionality is also available through the context panel. Here's the differential equation. You will find classify the ODE here. And what you just saw was Bernoulli. But Maple also launches this help page for solving Bernoulli equations. And in this help page, you see a stepwise approach to implementing a solution to the Bernoulli equation. Further along in the course, one studies linear constant coefficient non-homogeneous differential equations. This one models a driven damped oscillator. That's why I'm taking derivatives with respect to t, and I'm using the overdot to represent the derivative with respect to t. Let's see what Maple does with this initial value problem. I'm going to make use of this tool called the ODE Analyzer Assistant. It used to be up here with the assistants. It's now called a tutor, now listed with the tutors. It's still called an assistant, but it's now listed as tutor. So let's see what that tool looks like. We can access it from the context panel. You can solve the DE, which would give you the general solution to arbitrary constants. Solve interactively. It brings up the tool, it's still called ODE Analyzer Assistant, and you have an option of adding initial conditions. You can even add simple boundary conditions, but let's do the initial conditions. Y at 0 is 2, and then this is a drop down, so that's Y prime at 0, negative 1. Add that in, click done. Okay, so now you have a problem that can be solved numerically, but it clearly can be solved symbolically. When you click solve, you get the solution in this window. If you want to see it in a bigger window, you click here. So there's the solution, and if you click plot, you get a graph of y. You can modify that graph if you like. Here, going to plot options, do stuff like this. Make a copy of y, change y to y prime. Click done. Click plot. You now have a graph that shows both y and y prime. Right here, if you check this box, you will see the commands. You'll see the desolve command that solved the problem and the plot command that drew the graphs. When you click quit over here, you can return that solution, you can return the graph, you can return the Maple commands, or you can return nothing. So here is a tool that lets you see a solution, see its properties, without having to mess with any kind of syntax. Now, if you want to work through the solution in a more stepwise fashion, let's first recover what we learned from the analyzer assistant. Equation, data. I've just hit it with a desolve so we can see what the solution is, and here's a graph. But now let's work through the steps. Now we can get a fundamental set. Make the how do you get that? Make the exponential guess. You plug that into the homogeneous equation, do a little bit of algebra, you factor out the e to the lambda t, and you're left with the characteristic equation. You solve the characteristic equation with the characteristic roots. Each root gives you a solution, but these solutions are complex. How do you get these real solutions that Maple produced up here? Well, you use superposition. You take linear combinations. You add, divide by 2, subtract, divide by 2i. So now you have the two real solutions. For the homogeneous part, now you want a particular solution. So there is a tool for getting you a particular solution. There it is. How do you get the particular solution? Well, I'm going to use undetermined coefficients. So for undetermined coefficients, you make a a guess. You look at the right-hand side, you look at the driving term, and from that you decide on what the template should be. It has two constants that you need to determine, and the way you determine that is you plug that into the differential equation and choose those constants to make this an identity in T. Well, Maple has a solve identity command, and you get A and B. In the old days, the way I learned it, you collected coefficient like terms, and therefore the coefficients had to agree. Therefore, you get a pair of equations like that, which you would solve, and you get the same two values for A and B. Okay, so you have a particular solution, and you see a way of obtaining it. Therefore, you can get a general solution. There's the general solution. It brings in two new constants, capital A, capital B. The data is what determines those two constants. Now, I wrote some code here to go up where the initial conditions were written, grab the pieces of those equations and put them in the right place. These are the two equations that you would have to solve for A and B. Solve for A and B, put them into the general solution, and you got one more step. You've got to compare that solution, that stepwise solution, to what Maple got with its desolve command. I think there's about 15 steps in that solution, and any little arithmetic mistake is going to send you off to Never Never Land, wandering around doing arithmetic that you don't really want to do. I think this is a very useful way for a student to begin learning what the process is, what the steps are, and in a future webinar, probably later the same month, we're going to take a look at the student ODE package, which is new in Maple 2021 and was put into the context panel in Maple 2022, and some of the stepwise stuff is actually provided for you by Maple itself. There's another problem that might show up in a differential equations course, and that's the solution of linear systems, constant coefficient, first order. Here's an example. So we have a pair of differential equations of that type, initial conditions, and a first solution that we can obtain is via the ODE Analyzer Assistant. So here I've brought the two equations down with a comma in between, so I have a sequence of equations. If I make use of the context panel and select Solve the DE interactively, it will bring up this ODE Analyzer Assistant. If I would like to add initial conditions, I click Edit. Drop down here says X at 0, and I will give the value 3/10, and you click the Add button. This drop down lets me select Y at 0 is 0. Add, done. I now have an initial value problem I can solve numerically, but I can certainly solve it symbolically. Click the Solve button, and I get a solution. If you want to see it in the bigger window, you can do that. If you want to see the graph, you click Plot. And what you have is a plot of X, and it's on the default domain 0 to 10, and you see these great big numbers because X contains an e to the 7t, so you're going to get big numbers. You can fix that. You go to Plot Options, certainly limiting t to not 10, but 1. And while we're at it, let's make a copy of X and change it to Y. And now when we click Plot, we will get a graph of X and Y. If you check this box, you'll see the Maple commands. Desolve gives you the solution. There's a plot command here that tells you how to get the plot. When you click quit way over here, you can return the solution, the graph, the Maple commands, nothing. Let's return the solution. Okay, so here is the solution that we found with the ODE Analyzer Assistant. We obtained one orbit in the phase plane, but let's draw a phase portrait. So I'm going to use a task template, and I've shown you where the task templates live. Here is the path to the task templates. This is the one I picked. It's already embedded. I filled in some of the fields to save a bit of time. This determines the size of the plot window. Here are the differential equations. X dot equals this, Y dot equals that. Equilibrium or critical point, there's only one, 0, 0. And a numeric integration is going to take place for the trajectories. So the parameter on the trajectory is t, and I'm going to integrate forward and backwards so I get a complete trajectory. When I click Enter Data, I get a direction field. The green dot is the equilibrium point, and each time I click on the graph, I get an orbit through that point. So if you click on enough points, you'll get a phase portrait, and from this phase portrait, we can guess that the origin is a saddle point. Another way to solve this problem is to obtain a fundamental matrix. Well, if you have a way of obtaining a fundamental matrix easily, you can do this. Let's see how Maple deals with the fundamental matrix. So you need the system matrix. Look at the coefficients, 3, 12, 4, minus 5. You make a matrix. I'll show you over here, I used the matrix palette. The size of the matrix, 2 by 2. You insert a template, fill it in. There's my matrix. But I want to give it a name, A. So assign to a name, this is where you put an A. Okay, so the matrix A. Now I want E to the AT. So here's A. I'm going to go here to Control Panel, Standard Operations, Matrix Exponential. Pop-up says, what do you want the variable to be? T. All right, so here is a first attempt at a fundamental matrix. But it's not as simple as it could be. So you've got to do this in 2 steps here. First, we do an expand, and then we do a combine. This is about the best that you're going to get. So let's give that a name. PHI, phi. PHI, it's typically what they call that fundamental matrix. How do you use the fundamental matrix to get a solution? So fundamental matrix, period for non-commutative multiplication. And then you put the initial vector here. The initial vector was 3 tenths, comma, 0. There's the solution. I wonder if we can compare that in any way to the solution we got earlier in this form. So I think I'm going to do a copy paste just so that you can make a first comparison. Let's paste that in down here. Okay, 3/40ths e to the minus 9t plus 9/40ths e to the 7t, and y is minus 3/40ths e to the 9t, 3/40ths e to the 7t. So we got the same solution as we got before. Now the typical textbook that treats this material solves these problems with Eigen Pairs. What do we mean by that? We need eigenvalues and eigenvectors. Okay, so we need A. We write the name A and hit the enter key. So there's the system matrix. We want eigenvalues and eigenvectors. So let's go here to the context panel, and you'll see eigenvalues, etc. We're going to get eigenvectors. That returns a vector of eigenvalues. And the order of the eigenvalues here is the order of the corresponding eigenvectors here. So 3, 1 is an eigenvector, minus 1, 1 is an eigenvector, and you want to get them as vectors. So here's how you can do that interactively. Select element 2. That's the matrix. Then select elements, split into columns. So now you have a list of vectors. If you give this a name, like capital X, so assign that to a name, then you can reference each of those vectors as x1 and x2. So what does the general solution look like? Well, it's a linear combination. So I need a coefficient A, and then I need e to the first lambda t times this eigenvector. So you can type the letter E that is not the exponential E. There are several ways to deal with that. You can make use of an E, an exponential E. I've got in my favorites palette, which I put there by going to common symbols. That's an exponential E. If you right click on it, you get the option add to favorites. So you can either get it from common symbols or you can get it from your favorites if you populate your favorites. Or you can press the escape key, which brings up a list of things that start with E, and select exponential E. That is the exponential E. So let's put the appropriate exponent, 7t. Right arrow to come down. Let's put a space for implied multiplication. And let's put x sub 1 plus another constant, b, another e. Do an escape. I'll do exponential e to the negative 9t. Come down, a space, x sub 2. So there's the general solution, and I'm going to give that the name, uppercase Y. Now we got to do the initial data at t equals 0. So we want to put t equals 0 in here to y. So let's do a substitute into. Let's substitute into y. And we have this vector, which I'll call y0. So I'm going to give that a name, y. So this y0 has to equal the initial data. And here's y0. And it has to be set equal to 3 tenths 0. All right, we want to equate those two vectors. So let's use the equate option in the context panel, and that gives us the appropriate equations that we solve for A and B. So let's do a solve. Simplest solve will work. there are the two numbers A and B, and if we do a substitute into y, we should get the solution. Is that the solution that we had before? Well, let's see if we can grab the solution from here, say. Do a copy paste and we'll put it in under here, and we'll take a quick look to see if these are the same. 3/40 e to the minus 9t, 9/40 e to the 7t, minus 3/40 e to the minus 9t, 3/40 is e to the 7t. So we've gotten the same solution in different ways. We've done it with the fundamental matrix. We've done it stepwise. We've done it with the syntax-free analyzer assistant. And in the student ODE package, there is, again, a stepwise solution prepared by Maple that does the eigenvalue or the Eigen Pairs solution. There's another tool that's worth knowing about, and I'll use it illustrated by the Lotka-Volterra predator-prey model. So, you saw tutors, DE tutors. There are two. This one called DE plots. Okay. Now, you can launch it from there. This button will launch it. This is the tutor. Okay. It has a collection of built-in models. Lotka-Volterra is one of them. And then you click DE plot. Up pops the tool. Here's the model. You can change the parameters. The way you would change the parameters, you would type the data in over here. Initial points. Here are the initial points. 2 have been selected. Okay. Now these orbits would close if we increase t from 10 to about 14. Do another display here. Okay. So you have other options that you can change the colors and the density of the arrows and what the arrows look like, a whole bunch of different kind of arrows. So here is a tool that will allow you to explore many of these standard models that you find in differential equations books. If you go back here and pick animate, then the drawing of the orbits is animated. I think if you press play, so you can see how the orbits follow the arrows. So just another tool worth knowing about. Autonomous nonlinear system. So here's an example, and we are to analyze this, we need to find any equilibrium or critical points. Then we want to get a phase portrait, and then we want to linearize and determine analytically the nature of each critical point. So let's go here to a page where we can do this work. So let's find the equilibrium points. Make a list of the right-hand sides of these two equations, because you're looking for the points where the derivative goes to 0, so you're solving equations. So you have this and that. Maple's solve command will take care of the equals 0. So I've used the context panel, solve, got 4 solutions, and this sequence of 4 solutions I give the name S. To get to phase portrait, we can use a tool that we've already used, the task template. I've filled in some of the data to save time. This sizes the plot window what I did was to look at the solutions and just make sure I captured all the critical points. Here are the critical points. I'm going to use a numeric scheme to integrate for each trajectory. This minus 3 to 3 says I'm going to integrate in both directions. So I get a complete orbit. Into this data, you get a direction field, you get the 4 green dots are the 4 critical points, and each point that you click on, you get an orbit through it. If it would listen to my clicks, I think I have to give it a little bit more time between clicks. I tend to do that too fast. Okay, so what we're discovering here is that the origin appears to be a node out. So it's a repeller. This appears to be a node in, so it's an attractor. This appears to be a node in, it's an attractor, and this appears to be a saddle. To determine the nature of these critical points analytically, we linearize. Let's do that here. So want to load the student linear algebra package, we'll need that. Then recall that we have this list of right-hand sides. That's what I've brought back here. There is a Jacobian matrix command in the context panel that gives us the general Jacobian matrix, and I assigned it the name JM. And then evaluate this general Jacobian matrix at each of the 4 critical points that we computed here, S1 through S4. I've used the evaluation template, so I'll show you where that is. I have a copy of my favorites palette. I get it from the expression palette. It is this icon here. It's really the evaluate command. And if you want to put it in your favorites palette, you right click and add to favorites. So Jacobian matrix at S1, S2, at S3, and S4. The eigenvalues are on the diagonal. They're both positive. They have a node out repeller. For a lower triangular matrix, the eigenvalues are again on the diagonal. They're both negative, node in, attractor. Both eigenvalues are negative, node in, attractor. Here you have to compute the eigenvalues. So we make use of the context panel, student linear algebra. There's your eigenvalues. The eigenvalues are 1 here, definitely negative. This one here, well, let's see, square root of 64 would be 8. So that would be positive. This is definitely positive. This one is negative. You have a saddle. This next problem you might not have in a first course. It might be something that would turn up in a second course. A regular perturbation for this initial value problem. It's nonlinear. Y double prime here. Parameter P will be the perturbation parameter, and we're going to try and find a solution in terms of a series in the parameter P. This showed up in Maple Primes a while back. Here's a link to where the question arose, and I've treated this in my advanced engineering math book, so it's not that far removed from the normal course of events. When the problem appeared in Maple Primes, there was a solution posted by a person who signed his name as Maple Math Mat, and it's a coded solution. Right? It's got all commands, okay, and it's in 1D linear math, very hard to read. I find things like diff and so forth not really convenient to read. Anyways, it works, but I want to show you a syntax-free solution. But before I show you the syntax-free solution, I have a visualization that will help you understand what's going on. In this visualization, the slider controls the parameter p. The black curve is the perturbation solution, took it out to 3 terms. The red solution is numeric. That's as close as you can get to an exact solution. Now, as you decrease the value of p, the perturbation solution and the exact solution are close for a much longer time. As p gets larger, the discrepancy or the error between the two gets greater. And you'll notice as you move the value of p, both solutions move because both solutions depend on p. Okay, here's my syntax-free solution. It's been laid out to save some time. You don't have to watch me type stuff. Differential equation. Give it a name. Build the perturbation function. A of x, b of x times p. So this is the p to the 0 term. This is the p to the 1 term, and this is the p squared term. So I'm going to just take these 3 terms, and I make this a function. Next, substitution of this in for y. So I write y equals f, and I do a substitute into. And so you get all of this. Differential equation now looks like this. Series, all right, we have this here. We do a series, get it from here, series. And the pop-up that you get, the expansion point is p equals 0, and the order is 3. And this checkbox takes away the big O term. So here is the series. Okay, here's your p squared. Here's your p to the 0. And I want the coefficients of p. So you can get that from here, coefficients, right? Coefficients. This is the coefficient of p to the 0. This is the coefficient of p to the first power. This is the coefficient of p to the second power. And I give that sequence the name q. Now I'm going to solve the differential equations represented by each of these coefficients. So here's the first member of q, that's this term. And I apply both conditions. The non-homogeneous condition is going to be handled by A. Right click, solve the DE. Here is the result, and I make this a function. Second coefficient, that's Q2, and I use homogeneous data for the conditions. Solve that problem, get this expression for B and make it a function. Do the same thing for the third coefficient. It's a differential equation. Here's the data for it. Solve, get this expression, assign as a function. When you write f, each of the functions a, b, and c of x are now known to Maple, and Maple puts them in, and this then is the perturbation solution that I used in that visualization. This is the p to the 0 term, this is the p to the 1 term, this is the p squared term. Now I think we have time for one more problem. This is number 10. The Sturm-Liouville eigenvalue problem. This is a pretty tough problem, not simple. And the solution that I'm going to present requires that Maple can provide a general solution to this equation. If Maple cannot provide a general solution to this equation, if you have to solve this equation numerically, it's a whole another story completely. I've dealt with that in other webinars, but I'll show you what you can do here when Maple can solve this equation analytically. So let's go over here to a page where we can do some work. Let's get started with some initializations. So I'm going to load student linear algebra, load student calculus 1, loading the plots package. Just click this exclamation point. Okay, differential equation. Notice that I made sure to use the exponential e here, the differential equation. And I give the equation the name dE. This is the first boundary condition called BC1, and this is the second boundary condition called BC2. And then I do one little typesetting thing. I want the functions Bessel J and Bessel Y, which are going to show up in the solutions, to write on the be presented on the screen as J and Y. Okay. Now I've used the command, but you can use the typesetting rule assistant in the view menu. So you go here to the view menu, typesetting rules. Here you bring this tool up, and you can do the same thing here interactively by finding the item you want and telling Maple, here, do this. Rather than spend time redoing what I did with a command, I'm going to move on to the solution. So this is the thing that amazes me, is that you can solve what's really a difficult problem in a syntax-free manner. Right. Type DE, hit the enter key. There's the differential equation. Context panel. You solve the DE. There's the solution. Now this J sub 1 is a Bessel function. This is Y1, that's a Bessel function. That's what this command accomplished. And then I want to make this thing a function. So y of x is now this function. And I wonder if I want to re-execute this stuff. Okay. To apply the boundary conditions, you've got to be clever. Here are the two boundary conditions. Because the boundary conditions are given in terms of y of 0 and y prime of 0, and I made this exact solution a function, y of x. When I type BC1, BC2, Maple uses the information about y of x and gives me the two boundary conditions with all of that information inserted. And you see here at the comma, that's the first boundary condition, that's BC1. And you over here, this is the BC2. These are homogeneous equations in the constants C1 and C2. So I want to represent it in matrix vector form. So that's why I used or installed the linear algebra package. So you go down here to student linear algebra, constructions, generate matrix, and we get the matrix of for the coefficients C1, C2, and the right-hand side vector, which is 0, 0, the 0 vector. Now, I only want to look at this matrix. So I pick that out by select element number 1. Now I have the matrix. The coefficients C1 and C2 are going to come out to be identically 0 unless this determinant, the determinant of this matrix, is 0. So I get the determinant of this matrix. And this is the determinant of that matrix. Only when that determinant is 0 will I have non-zero values for C1 and C2. Those are the eigenvalues for this problem. So I'm going to solve for the zeros by using Student Calculus 1, find roots. All right, you saw that there, find roots. In Maple, find, well, maybe I'll do more than that. I'll show you. Student linear algebra. Here, I'm going to be here. Student linear algebra. Student calculus 1, find roots. You get this pop-up. And I went in a range from 0 to 100. And I checked this box, calculate numerically, because there's no way you're going to get an analytic solution. And if I'm not mistaken, I have a picture of that right up here, right? This picture right up here tells me how to do that. Okay, then I gave this list of eigenvalues the name capital lambda. I'm not done yet. I want to get an eigenfunction. So I write the first boundary condition. You pick one of the boundary conditions. Pick one of the boundary conditions, which is this. And I want to put into this one of these eigenvalues. I'm going to just pick the first eigenvalue. Okay, so I use evaluate at a point. Let's bring that over here, evaluate at a point. Okay, evaluate at a point. And I think I showed you here what I did. Lambda is capital lambda of 1, so it's this number here. And everything collapses to this equation. And I can solve for one in terms of the other. So if I go up here, I think there's an isolate option. So I think if I select C1, yeah, see isolate? Click on that and you get C1 equals a multiple of C2. So if you replace C1 by this expression by using the substitute into, you will have this version of the first eigenfunction. And eigenfunctions are only determined up to a multiplicative constant. So I'm going to set C2 equal to 1. So I did that here. And then because I'm still looking at lambda, I made it lambda 1. This is my eigenfunction. So I have actually determined an eigenfunction for this problem. And then I drew its graph, and you can see I used the plot builder to draw its graph, and there's the graph, the eigenfunction. Now I've got just a brief minute here. I think I'm going to do a better job showing you how to use this typesetting rules assistant. Okay, so this drop-down contains a whole bunch of abbreviations and assistants. I'm looking for Bessel functions. I'm looking for Bessel function. Bessel function. Bessel function. Bessel. Okay. Bessel J. All right, so you select Bessel J. and it says this is the Maple syntax, this is what it will display like, and checking these two mean that both on input and output, that abbreviation stands for Bessel function. So that's how you make the use of the typesetting rule assistant. It does what that command did. And if you want to see if you were successful or not, what you could do is type J lower 1 of X. And then let's get a series for it. Series, let's get the formal power series about 0, dummy variable K. And if you remember what your Bessel function looks like, that symbol, J sub 1 of X, has now been set to the Bessel function.